Hello everyone, my name is Brody Lauer, and I'm the Program Manager for the design of the Localized Initial Lunar Architecture Complex, designed at the University of Illinois at Urbana-Champaign. This architecture is designed to be a durable, reusable, and low-mass surface habitat with the purpose of enabling and expanding Artemis mission capabilities at the lunar South Pole. With operations beginning in 2028, this architecture facilitates sustainable lunar activity in the late 2020s and early 2030s, as well as technology demonstration and preparation for future Mars missions. In support of these goals, the architecture is designed to enable exploration and science activity for NASA, while also providing a foothold for commercial and international development. The core mission requirements and constraints were derived directly from the RASC-AL theme statement. These requirements include the capability to support a crew of 2 astronauts at the lunar South Pole for a nominal 30-day mission, while doing so with a habitat that is low mass and reusable over multiple missions. In order for this habitat to be an effective asset of the Artemis program, it must be ready for first use in 2028 and require no more than $1 billion in funding per year, including delivery to the lunar surface. The LILAC architecture meets or exceeds these core requirements with a total launch mass of under 6,000 kilograms even after the inclusion of a 1,000 kilogram mass margin, and a total program cost of under $6.3 billion over the 7-year program. In addition to these core quantitative requirements, the architecture is also purpose-built to expand crew capabilities for science and exploration on the Moon, while also developing the technologies and procedures that will be needed for missions to Mars. In addition to the core theme requirements, LILAC is also designed with consideration of the requirements, interfaces, and core objectives of the Artemis program. Since the Artemis program aims to achieve sustainable lunar exploration and development, which includes the evolution of reusable lunar landers, LILAC is designed to be deployed directly to the lunar surface from a commercial landing vehicle, permitting the lander to return to orbit for reuse if the capability is available by this time. Additionally, LILAC meets or exceeds Artemis program design requirements and guidelines written for the human landing system, particularly with regard to survivability in darkness and internal layout organization. Interface with other Artemis program elements and guidelines were also used in the development of the LILAC architecture, including selection of an atmospheric pressure and composition, which are in line with recommendations written for lunar operation and EVA, and a communication architecture operating at frequencies specified in the International Communication System Interoperability Standards for Lunar Systems at strengths exceeding the minimum required guidelines. LILAC, the Localized Initial Lunar Architecture Complex, is a multi-element architecture which is launched and delivered as a single unit and consists of a main habitat, a freestanding solar array tower, the Surface Transportation and Engagement Mechanism, or STEM, and the Robotic Outpost for Operations and Transportation, or ROOT. The STEM provides transportation and remote surface manipulation capabilities, while the ROOT provides operational support and unpressurized elements of the infrastructure needed to support crewed operations, primarily communications, power generation for lunar darkness, and storage of cryogenic tanks. The habitat itself is transported in a stowed configuration, but is then deployed using flexible extensions in the center of the habitat and around the airlock, which dramatically increase the habitable volume available to the crew. The total launch mass of this architecture is 5,970 kilograms, with the inclusion of a 1,000 kilogram mass margin, which is around 20% the effective mass limit of 5,000 kilograms without margin. Therefore, following the addition of this mass margin, LILAC is still within the required launch mass limit of 6,000 kilograms given in the theme requirements.
LILAC is designed with the potential to be launch vehicle and lander agnostic, using a commercially procured launch vehicle and lander with the NASA Launch Services Program. In the reference case, payload delivery occurs in 6 phases. Phase 1 consists of a New Glenn rocket launching LILAC and the Blue Origin descent element of the National Team HLS to orbit. Shortly after, Phase 2 occurs, where the upper stage of the New Glenn rocket begins a low-energy transfer burn. Since the New Glenn rocket is 250 meters per second short of completing the burn, Phase 3 then occurs, which includes the lander finishing the low-energy transfer burn to capture into polar low lunar orbit. Once in position, Phase 4 occurs, When LILAC lands on the south pole of the moon, Instant begins to dismount the habitat from the lander deck to the lunar surface. After this initial deployment, Phase 5 begins, which includes lunar operations as STEM walks route and the habitat to the deployment zone. Finally, Phase 6 consists of the full deployment of LILAC, which marks the beginning of operational service for the habitat.
The habitat is a horizontal expanding cylinder consisting of two end caps and a deployable section in between. This design results in a high usable volume to mass ratio when deployed, while taking into account other usability factors, including floor plan and ease of deployment. It also provides the minimum required volume for life support equipment when packed. This allows the habitat to be minimally functional in the event of problems during deployment. Furthermore, the packed configuration allows the habitat to fit in a 5-meter diameter fairing for transport to the lunar surface. The habitat has a volume of 55 meters cubed when deployed, and a diameter of 3.2 meters. The habitat has a total length of 7.8 meters when deployed, and a length of 2.4 meters when stowed. The mass of the habitat structure is 2,330 kilograms. The deployable section consists of radiation and MMOD protection layers near the exterior, with multi-layered insulation sandwiched in between, as well as a structural bladder closest to the interior. The deployable section layers are Z-folded for packing and are unwound during deployment. The total thickness of this section is 0.05 meters. The end caps consist of advanced MMOD shielding and an aluminum outer shell, and include structural reinforcements for root supports. The total thickness of this section is 0.1 meters. Internally, the structure is covered with aluminum honeycomb panels. The habitat protects the crew from galactic cosmic rays. The radiation dose from GCRs is 13.1 milligrays per mission.
As a bit of an overview, shown here is a diagram of LILAC's stem and root system. The stem is the crane, as indicated at the left of the slide, and its legs are the stem outriggers. The root is attached to the stem and holds onto the payload, which in this figure is LILAC's stowed habitat. One of LILAC's biggest innovations, the STEM, or the Surface Transportation and Engagement Mechanism, is a 200-kilogram crane-like structure based on NASA's LSMS. STEM is used to transport the habitat and subsequent payloads from the lander to the lunar surface. STEM's 280-kilogram outriggers consist of telescoping trusses that ensure that the system does not tip while carrying and transporting payloads. On the right of the slide is a plot of STEM's operating conditions, where the black indicates the location of the outriggers. The payload position, shown in blue, is always within the operating envelope, shown in green. The stem is directly attached to the root, or the Robotic Operations Outpost for Transportation, a 180-kilogram frame that holds onto the habitat and supports it during the transportation process. The root provides greater reusability and versatility in other payloads that may also need to be transported. The stem and root system can operate either autonomously or manually, and thermal blankets are placed around all the moving parts in order to mitigate effects of both thermal gradients and lunar dust intrusion. The stem and root system transports payloads across the lunar surface by walking, essentially by alternating movement of the root and the payload, and then the stem itself. The cycle begins with the stem moving the root and the payload, which is specifically the habitat in the sequence shown at the center of the slide. Then, the stem uses the root as a pivot point to reach a new location. This repeats until the payload is in its final desired location, at which point the stem lifts the top of the root by the elbow and the bottom of the root with a cable to flip the payload into its final position.
The communications architecture is built to follow the International Communications Systems Interoperability Standards Guidelines in order to be compatible with existing lunar communications networks, and to take advantage of cislunar space platform relays such as the LunaNet Communications Network planned under the Artemis program, and the Gateway Relay Communications System in NRHO. Under this standard, proximity communications with the XCMU suit use a UHF band frequency, while communications with the orbiting relays operate in the S-band and Ka band. Therefore, the LILAC communications architecture uses UHF band WIP antennas for surface communications and dual gimbaling parabolic antennas for high-gain communications, but also a small S-band patch antenna for acquisition of signal to overhead relay platforms when the high-gain antennas are pointed to the horizon, with other relays outside the field of high-gain antenna field of view. In addition to the standard ICSIS communication frequencies, LILAC also uses an optical laser communications module derived from the unit developed for the Orion spacecraft, which enables ultra-high data rate communications of over 250 megabytes per second direct to Earth or to an orbiting platform, enabling the streaming of 4K video from the lunar surface. In total, this entire system has a mass of 40 kilograms and is mounted on the root to provide immediate and versatile access at all stages of the mission.
The atmospheric revitalization system serves to monitor and maintain a healthy environment for the crew and their mission. Starting with oxygen generation, the reversible fuel cell produces breathable oxygen for the habitat, as well as hydrogen, which will be used later. Next, a low-power 2-bed temperature swing bed captures exhaled CO2 from the crew. Then, the Sabatier reactor reduces this CO2 along with that hydrogen from earlier, creating water, which is fed back into the water recovery and management system to be used for electrolysis and to continue the cycle. Several other systems for CO2 reduction, such as lithium hydroxide, and for oxygen generation, such as static feed water electrolysis, were considered, but these were ultimately decided against as they did not efficiently achieve mission parameters. Beyond that, the cabin air assembly handles temperature and humidity control, and the trace contaminant control system prevents the accumulation of harmful particles in the atmosphere. Finally, the atmosphere composition monitoring assembly records atmospheric conditions, and cryogenic storage is used for the storage of nitrogen, hydrogen, as well as oxygen.
The water recovery and management system is comprised primarily of cascade water distillation, volatile removal assembly, and silver lactate. Cascade water distillation converts wastewater into distillate and brine, and the distillate is later filtered into potable water. It was chosen because of its high recovery rate and its non-reliance on Earth's gravity. The volatile removal assembly removes ionic and organic contaminants and was preferable to other technology like reverse osmosis because of its lower mass and lower power needs. Silver lactate is added to the water in order to remove bacteria and is preferable to other chemicals like iodine because it doesn't need to be removed later on in the water purification process. Using water walls as a water storage and radiation protection method was considered, but after a preliminary trade study, it was deemed inefficient for LILAC's particular habitat geometry.
Waste management on the habitat will be taken care of by a universal waste management system. This system will be adapted to lunar gravity for HLS, and flight heritage for the system should be achieved by 2028. Waste is stored for disposal on the surface for three main reasons. The first being to prevent contamination of the habitable environment. The second is to reduce mass by removing processing hardware from the habitat. And the third is that the long-term buildup of waste can be used for radiation and dust protection. Deployable walls are also contained within the system and are used to contain odors and contaminants. These walls are made up of the same low-mass materials as the deployable airlock.
To compile a reasonable consumable breakdown, the team studied different eras of human spaceflight research, ranging from retired programs such as Apollo and Shuttle to active endeavors such as analog missions and the ISS. After reviewing these sources and reviewing with ALSAT, we find the three largest mass contributing categories to be water, atmosphere, and EVA consumables. The numeric breakdown can be seen in the table to the right, as is the pie chart of the distribution of mass. Food comes in at about 117.5 kilograms, with an emphasis on dehydrated packets and a buffer for supplementation in the form of vitamins and radiation protection. The total consumable mass per mission comes out to be about 700 kilograms. A crew resupply will occur prior to or at crew arrival to the lunar surface, which is divided up across 2 smaller landers per trip.
The main airlock to the habitat is 280 kilograms. It utilizes a deployable design to expand like an accordion from a packed length of 13 centimeters to 3 meters. This length allows both the crew members and additional hardware to ingress or egress. Immediately following the primary airlock is the donning and doffing area for both the astronauts.
The first zone of the habitat is the donning and doffing zone. The key elements of this region include 2 compartments to the size designated by NASA standards, dust mitigation measures following EVAs, and the capability as a secondary airlock. The lattermost point was made following judges' feedback to create a backup plan in case the primary airlock door or the primary airlock itself experienced some variation of failure. Therefore, the addition of a secondary pressurized region mitigates such a risk while still providing enough space for suit outfitting and maintaining dust protection. Physically speaking, this means that the first and second zone, to be discussed in the following slide, are separated by a membrane identical to the inflatable region and an airlock door. The second region is referred to as a life support zone. Key elements include atmospheric revitalization, water recovery and management, the universal waste management system, as well as the general storage units. Primary design motivators included consolidating ECLS hardware to concentrate noise, as well as create a shelter in case of a solar particle event. In this scenario, the crew can situate themselves within the hallway between ECLS hardware to minimize the radiation experienced. Lastly, the toilet is located near the airlock to minimize odor and be contained in an expanding accordion structure to optimize privacy. This particular emphasis on the toilet's surrounding region was motivated by HLS requirements as well as judges' feedback. The final region is where the crew carries out a significant portion of their day-to-day activities. The key elements include the dining region paired with the food preparation unit, sleeping quarters comprised of Apollo-style hammocks, and a science workstation. The design of this particular region stems from initial research into analog missions and associated space architecture. The zone is divided up into regions based on primary functions, dining on one side, sleeping quarters on the opposite, and a workstation occupying the node. Simulating real rooms may help cope with isolation in confined spaces, given they more closely resemble normalized living quarters on Earth. Furthermore, each section uses stacking techniques to optimize horizontal space. The water dispenser, oven, and fridge are all stacked within the food preparation unit. The table can be folded down when not in use, and the hammocks were oriented in a bunked manner. Lastly, the bulk of innovation from a crew accommodations perspective is located in the science workstation. The shelving units underneath the desk, for instance, are all in accordance with ISS experiment sizes. Therefore, this location can house various scientific experiments, in addition to the desk and wall space available for various storage needs. Furthermore, 2 monitors are fixed to the wall above the desk and are connected to a camera on the outside of the node for continuous live stream when the crew desires. This concept was actualized to resemble a window while avoiding the significant radiation risk an actual aperture would have posed. Once again, the majority of efforts in the versatile habitation zone were focused on minimizing isolation effects and creating a comfortable environment for the crew.
LILAC's primary source of power is 2 18-meter squared area solar panel arrays on a 10-meter tower that is connected to the habitat. These tower panels are capable of producing 10 kilowatts at a mass of 90 kilograms, and the panels themselves also fold upwards to stow. The solar panel's tall height allows protection from the lunar dust, as the speed necessary for the dust to be kicked up is 5.7 meters per second, and not possible to be generated during an EVA. Its height also ensures that the shadowing from the lunar terrain does not infringe on the generation of power throughout the duration of the mission, as well as allowing it to be easily modified to enhance its capabilities with additional hardware for future missions. During periods of continuous darkness, regenerative fuel cells will be used instead of solar panels.
While the solar arrays provide high power to the LILAC architecture at a low mass, they are not capable of powering the system during the deployment process before the solar array tower is raised or during periods of darkness when the sun is obscured by the horizon. Based on the requirements established for the human landing system, this architecture is designed to operate at full ECLS capacity for at least 50 hours of darkness, while additional duration can be achieved through decreasing power consumption or increasing energy storage capacity at the beginning of the mission. To provide the 250 kilowatt hours of power needed for these operations, LILAC includes a regenerative hydrogen and oxygen fuel cell in the root. Additionally, since this fuel cell can also perform electrolysis functions to regenerate propellant, it could also be used to create the oxygen for crew consumption in the habitat and support the atmospheric revitalization system. However, since this technology has relatively low TRL, a non-regenerative fuel cell is also designed in the early stages of manufacturing and integration in case the regenerative fuel cells do not mature in time. If these cells must be used, the water produced can still be used to save mass in water consumables, but require extra propellants for each lunar darkness cycle.
The thermal control system is sized to reject 5 kilowatts of heat from the habitat, which was the requirement obtained through the Advanced Life Support Sizing and Analysis tool and includes the effects of solar illumination on the exterior of the habitat. It rejects this heat through a 15 square meter pyrolytic graphite radiator, which is a flexible foil material used on the Merlin satellite, a joint CNS and DLR mission scheduled to fly in 2025. The internal mass of a single-loop thermal control system using HFE 7200 as the coolant was sized to be 230 kilograms through an analysis in the ALSAT program, while the radiator and supporting structure is an additional 100 kilograms. The radiator takes advantage of flexible capped-in heat pipes to roll up during transport and then unroll for deployment, reducing the area exposed for damage during transport and minimizing the stored volume, similar to the storage methods employed for the rollout solar arrays developed for the International Space Station and Gateway.
During a single mission, the crew performs 20 EVAs. To limit the amount of lunar dust the crew brings into the habitat after each EVA, LILAC employs multiple types of technologies. First, the astronauts use electromagnets to clean their suits. During ingress, the astronauts pass over their suits with a handheld electromagnet 3 times, once just outside the airlock, once in the airlock, and once in the secondary airlock. Electromagnets are used because while brushes used during the Apollo missions were ineffective at removing dust, tests on lunar dust samples have shown that lunar dust is very attracted to magnets. To protect against any dust that still enters the secondary airlock, the astronauts wear N100 masks and portable respirators once their arms are out of the XEMU suit. Finally, a wall separating the main habitation area from the secondary airlock reduces the amount of dust that can move into the main habitation area. In addition to posing a danger to crew health, lunar dust can also reduce the performance of radiators. So LILAC utilizes indium tin oxide paint, also known as ITO paint, to prevent lunar dust from sticking to the radiator panels. Using atomic layer deposition, ITO paint can be added directly to the thermal paint normally used on radiators. As this technique deposits a layer of ITO only a few atoms thick on the radiator, the mass of ITO in the radiator was assumed to be negligible. The ITO paint prevents electric charge from building up on the radiator, which prevents lunar dust from being attracted to the radiator. The radiator is also raised up above the habitat to decrease the likelihood that dust reaches the panels. However, ITO paint has a vulnerability where it could crack due to fatigue caused by opening and closing the radiator. Any cracks that form would allow dust to collect on the radiator. As shown in this table, to combat this, the number of cycles is kept lower, the bend diameter is kept higher, and the bend frequency is kept much lower than the experimental conditions used when the fatigue characteristics of ITO paint were tested in the paper Bending Fatigue Study of Sputtered ITO on a Flexible Substrate. Because the mission keeps these characteristics in the safe zone, ITO paint fatigue and subsequent cracking will not compromise the mission.
The timeline is broken into 4 key stages: design and development, fabrication, launch, and operations. Work on LILAC begins in 2022 with the system requirements review and early design and development. Technology maturity also occurs in the background from 2022 to mid-2026. Fabrication starts in 2024 Q2 with assembly, integration, and testing lasting till the end of 2027. In 2025, NASA Launch Services Program releases contracts for launch and delivery of LILAC to the lunar surface. By Q2 of 2028, fabrication, testing, and integration of LILAC are complete, and the system is launched to the lunar South Pole by commercial payload service provider in 2028 Q2. Following delivery, LILAC transports itself to the final deployment position using the stem and root system, after which the habitat is fully developed and is ready for habitation in 2028 Q2, thus completing the timeline. Cost is broken down to 3 key stages: design and development, fabrication, and launch. NASA's Project Cost Estimating Capabilities software
was utilized for the development of LILAC cost analysis. The constraints of staying within $1 billion per year from 2022 to 2028 with a 2% inflation rate starting from fiscal year of 2020 are satisfied. The total cost for design and development is $4.074 billion. Fabrication begins after 2 years of design and development with a total cost of $1.15 billion. Launch costs are $1.02 billion, which is distributed from 2025 to 2028 in conjunction with NASA Launch Services Program, thus spreading the cost of the launch over a 4-year plan. Total cost of LILAC is $6.246 billion over the total mission time, which is compliant with the constraints.
While there are technical, schedule, and programmatic risks in the LILAC design, many of the largest risks have been mitigated through careful implementation of mitigation strategies. During transport across the lunar surface, relatively high loads are supported by both the stem and the root, with the torque exhibited on the root structure when the stem lifts itself having the least structural margin. Therefore, to mitigate the risk that mass growth of the stem during development increases these loads to unacceptable levels, the solar array tower and any additional small cargo is designed to be attached to the stem base during transport, so that if the stem does experience mass growth, the cargo can be moved to the root itself and torques on the root will not increase. The second major risk is that the thin airlock material for mass minimization is punctured and leads to an airlock failure, which is mitigated by the inclusion of a secondary redundant airlock inside the main habitat structure. Both the regenerative fuel cell and the electromagnetic dust removal process have a risk of not reaching maturity by the time mission operations begin, so a heritage fuel cell at a lower mass efficiency is prepared for the mission, and a multi-stage ingress process for incremental dust mitigation is also used in the habitat design. Finally, there is a programmatic risk that departure from the lunar surface is delayed at the end of the mission due to rendezvous scheduling with Gateway, so a minimum of 10 days of logistics contingency is built into every mission in the LILAC habitat. LILAC, the Localized Initial Lunar Architecture Complex, is a low-mass, reliable, and reusable architecture which meets or exceeds all program requirements, while also adhering to Artemis program goals and expanding operational capabilities at the lunar South Pole. Thank you.